Okay, so for this little snip of a lecture, we're actually going to be finishing up this stuff about conditional independence and these Imaps, Bayesian networks in general. So this is probably going to be the final lecture in terms of that, but we are not done with graphical models. We're going to just move in some other directions. So today I'm going to just focus primarily on Imaps because I do think that's incredibly useful to understand this relationship between conditional independencies and the graph itself. And we talked about Imaps, and I'm actually asking you to go through a particular exercise involving Imaps in your homework. So I want to now just give you a feeling for what is an Imap and what's called a minimal Imap, and how to construct them. So I'm going to go through a couple of examples here. So the first slide I have is a repeat, and so this should be really familiar. This is from that simple network where we had that grade, SAT, difficulty, intelligence. And so it just actually took two nodes from that network, D and I, and it says, okay, well, these are not related at all. There's no edge between them. So these are, in fact, independent. But in this graph here, G2, they are linked. And in particular, D is a parent of I. So these are not conditionally independent. So the set of independencies, the Imap, is in fact empty. The Imap here, the independencies involve D being independent of I, and what I told you was that this is not a one-to-one mapping. So this empty set actually is a valid Imap for P1, but this one in fact is not, because it has an independency in here which does not hold up in this distribution. So this particular element violates this distribution. Now this point is going to be absolutely critical when we start to think about minimal Imaps now. So there's not a unique set of Imaps. Imaps capture the conditional independencies, but there could be some that are in fact left out. However, if there's one in the set that violates, then we have problems. So this is a trivial case, the one that I just showed you, which is not entirely useful for us in terms of gaining information about the independent structure from the graph. So there's two levels above this Imap definition. One is called a minimal Imap, and this one is a graph K is a minimal Imap for a set of independencies I if the removal of a single edge from K renders it not an Imap. Okay, so it's essentially the minimum set of edges for which it is a valid Imap. A removal of an edge would bring forth an independence between nodes, which is not valid in the distribution. So think about that in terms of the simple example, and now we're going to go through what it means to construct a minimal Imap. So this is a little bit of pseudocode which describes how to build a minimal Imap, and it actually has to do with ordering. So you can imagine that we have ordered set of variables here, and we're going to set G to be the empty graph over the nodes. You essentially pick a current candidate, U, that's the first node, and you look around, and that's actually going to have to be the root node. Okay, so then you take the second node, and that one is going to be, and you compare it with everything that's already been preceding it, and you ask the question, is it in fact independent? If it is not independent, if it violates the independence assumption, then you assign that particular candidate parent to that node, to that child node, and then this would be the minimal set. And then you add the next node in the bunch, and you look at all of the nodes that are already in there, and you say, is this a parent? Does this parent need to be here? If so, and you add it and so forth. Okay, so this is the pseudocode for it, which is rather technical, but it is. I'm going to walk through an example, which it follows the intuition that I am saying here, and also it follows the pseudocode. So let's go through an example. And so why not use the one that we're so familiar with? Suppose that this represents the true independencies. Okay, so we know that this is, in fact, an Imap for this distribution. Not only that, it is the true graph. I mean, there's nothing left to uncover. This is it. It describes every independency in the group. And let's say it's what you would call a perfect Imap. So say this is the truth. So now let's actually reason with this. So here's an ordering of nodes. Okay. So this is saying that we start with a bare graph and we say, okay, D is going to play the first node. Okay. Well, I haven't added anything else. You have to add another one in order to draw a line, right? So I is added next. Well, difficulty. So then you ask the question, well, does intelligence have to be apparent of difficulty? These two are actually independent of each other. We know that in the true distribution, so there doesn't have to be any line to connect them. And so when we add the next guy, S, we have to ask the question, well, S, is it a child node of the other two that we've already added in the graph, D and I? Well, we know the truth says that intelligence is a parent of SAT, so we include that line. We know that they're related. And we don't have to include difficulty because we know that if SAT comes from intelligence, it includes its parents, and given intelligence, we gain nothing from knowing difficulty. Okay? Now let's think about adding G. Well, G, if we add G, we have to ask the question, is D a parent? Well, certainly there would be an edge here. Intelligence, yes, certainly there is an edge there. And what about SAT? Well, if we know intelligence, we don't need to know SAT. They are, in fact, independent, so here are our edges. And finally, we add the letter, which I have, this should be L, apologize. So the letter. So if I add letter, I ask the question, again, do I need an edge here? No. No, no, because grade determines letter in the true graph, so we actually came up with the same graph, which is not exactly exciting, but this is the proper ordering which gives rise to this graph. And let's consider a different ordering, which is a little bit less intuitive. So now we're going to start with L. That's the first variable to enter the game. And SAT comes in next. Do I need a line from L to SAT? Yes, because, SAT is related to L through this path right here in the true graph. There's correlation here. So we actually have to put that line there. Because without any of this information, we do have to convey that relationship. Okay, and now we're going to add G, and we have to ask the question, well, is letter a parent of grade, and is SAT a parent of grade? Well, we know in the true graph that, in fact, they are correlated, and so that arrow is going to be important. And also we know that we don't have intelligence, so we have to convey this information about excuse me, about SAT and grade being related as well. They're certainly not independent, right? So we must fill in those arrows in that way. And now we add intelligence and we say, okay, well, here's intelligence, and what has to be apparent here? Okay, so let's start with grade. Certainly grade is going to be a parent of intelligence, and SAT is going to be also a parent of intelligence. They are related, most certainly. And what about letter? Well, letter, certainly we have this relationship here where intelligence gives grade, which gives letter, and that is important. But since we have this flow of information already embedded in the graph, we don't need that redundant edge. Okay, so finally, oops, here we are. We're going to add difficulty into the mix, and well, when we add difficulty, we have to ask the same questions. Well, difficulty, go through each one and ask the question, do we need an arrow? To letter, no. Well, first of all, the obvious one, we need it from grade. From letter, we don't need it because we have that flow of information that way. What about from SAT? Certainly we don't need it that way, but we do need to put actually an arrow here because of the, let's say, this arrow here, it prevents this flow. We know that there's a flow here of information, but this is essentially blocking that flow, blocking the active trail. So we need to actually convey this information, and we do that by putting this arrow from intelligence to difficulty. And that's it. And so this is a complete IMAP. And incidentally, since we have the tables for all of these conditional probability distributions, we could reason this out using the real probabilities to figure out what the dependencies are and how to draw the arrows. Okay, let's do a final ordering, and this is perhaps the most difficult one. We're going to start with letter, then we're going to add in difficulty. Well, certainly we need an edge there, okay? Then we add in SAT. Well, we know that SAT is related. There's information flow in the true model between the two, and also to letter. So they are in fact correlated. They are not. We know they're not independent. Let's add intelligence now, and intelligence, the same idea. Intelligence, we know. We need this edge from difficulty and letter and SAT. Those are the only variables in the model, and it's related to all of them. And finally, grade. And grade is in fact related to difficulty and intelligence, as in the model, and also to letter. We don't need the SAT arrow because we have this flow here, which tells us that they are not independent. And so we're all set. And incidentally, this graph here looks rather what you would call saturated. And this is almost a complete graph, meaning it's almost completely saturated. But it is a valid IMAP. It contains all of the independencies of this particular true network. Excuse me. So in these cases that I'm showing you, these simple examples, we actually know the orderings. We would know, for example, in this case, that this is pretty junky ordering because it ends up with such a saturated model that this is a little bit better in terms of node ordering. This is the best one. It gives the exact map. The problem is in true life, we do not know the ordering, so it is really just a little bit of a rolling the dice, and there is actually ways to infer these independencies doing an algorithm of this type on node ordering, and we're not going to go into that, but this is an excellent exercise to start to construct these, to think about Imaps in terms of going from the graph to the independencies. There is a such thing called a perfect map, which is the exact representation of the conditional independencies in a particular graph. So if you wanted to represent the joint distribution in the exact way, and say you knew it, you were a god, you knew it, you knew all of the conditional independencies, you may not be able to describe them in a perfect Bayesian network because of the assumptions that we have to make. So this question of perfect map, uh, can you represent all joint distributions with a perfect map? And the answer is no. Not every distribution has a perfect map, so that's important to know. So we're just going to stick with this minimal map as a way of, it gives us a little bit better handle on what the independencies are. It's certainly a little bit better than thinking about these trivial cases. Mm-hmm. So, without any constraint there, we always have these trivial cases that fit within the subset of independencies. And we kind of want to do a little bit better than that. Okay, thank you.